In this short video, we'll be investigating gearing and traction. We will use this Lego kit to construct a motor car which will hopefully drive up a hill. Note, this Lego kit was released in 1985. Lego may be expensive, but at least it's long lasting. We will build a simple chassis and then use a chain running across the axles to give us four-wheel drive. We will use a motor to power this vehicle. A motor comes from the term electromotive force. A motor is not an engine, and an engine is not a motor. This vehicle has a motor, therefore it is a motor car. Technically, this vehicle has an engine and probably shouldn't be called a motor car, and this vehicle should not be called a motorbike. Let's consider how gears interact with each other by counting their teeth. These gears have 8 teeth and 24 teeth, giving us a gear ratio of 1:3.
1, 2, 3.
These gears have 8 teeth and 40 teeth, giving us a gear ratio of 1:5.
1, 2, 3, 4, 5.
Worm gears only advance 1 tooth per rotation, giving us a gear ratio of 40:1.
Worm drive. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Gets to be a quarter.
There are many possible combinations of gears, giving us many possible combinations of gear ratios. Here we have 3:5. From the diameter of the wheel we can calculate the circumference. This will tell us how far the vehicle will move forwards for each revolution of the wheel. Let's look at the construction of our car, noting that we have changed our wheels to the ones we found gave us the best traction. Coming off the motor, we use an 8-tooth gear connected to a 40-tooth gear to give us a reduction of 1:5. In a second stage reduction, we use a worm gear to give us a further reduction of 1:40. These two stages combined give us a total reduction of 1:200, meaning for every 200 times the motor turns around, the wheels turn around once. The diameter of the wheels is 30.4 millimeters, giving us a circumference of 95.5 millimeters. When we divide this by the 200 turn reduction, we note that the vehicle moves forwards approximately 0.5 millimeter per revolution of the motor. Using these reduction gearing ratios will slow the vehicle down but greatly increase its torque, hopefully enabling it to climb steep slopes. Many students will recognize the numbers on the gear stick of a manual transmission. These numbers represent different reduction ratios of gearing within the gearbox. The higher the gear number, the less gearing reduction is taking place. First gear is low speed but high torque. Sixth gear is low torque but high speed. The usable traction on our wheels will be a function of the coefficient of traction times the weight of the vehicle. The surface of the notice board we are driving across consists of a lot of hair-like structures. How will adding weight improve our traction?
Okay, with this comb, the wheel touches one point. If I push down hard, you can see with more weight I get more points of contact, so more grip in points. So I've got to move.
How does adding weight affect the tyre's grip, especially a pneumatic tyre?
Okay, so with this balloon, if I just touch it, it has a very small point of contact. If I add weight to the balloon, I have a bigger point of contact.
The problem with adding weight while travelling up a hill is that some component of the weight will always be pulling the vehicle backwards. Considering the limited traction, our vehicle was quite successful, getting up a slope of approximately 40 degrees. Let's consider what we could have achieved if we could have changed the coefficient of traction. The coefficient of traction for a rubber tyre ranges from about 0.7 for driving on concrete to about 0.07 for driving on ice. Unfortunately, there is no data for driving on notice boards. Can we improve traction? With snow and ice, we can modify the surface of the tyre with chains. Equally, with notice boards, we could also modify the surface of the tyre. Coefficients of traction are typically between 0 and 1. However, the coefficient of Velcro is 6.0. What can we do with a coefficient of traction of 6.0?
Ready, set, go.